When it comes to equilibrium reactions will essentially proceed until they reach equilibrium. And at equilibrium, although the forward and the reverse reactions are still occurring, the rate of the forward equals the rate of the reverse, such that it appears that the concentrations are staying constant. It appears like the reaction isn't happening. If the reaction actually is happening, it's just that the rate forward equals the rate of reverse, and so the concentrations appear to be constant. For two different starting materials for the same reaction, you will not end up with the same concentrations at equilibrium, but you will end up with the same mass action expression, the same equilibrium constant expression. Numerically, it will be a constant regardless of what you start with. And we'll be plugging some numbers into the equation to prove that before too long if you haven't already. But what we want to look at is just sort of qualitatively what happens to the dynamic equilibrium reaction if it is at equilibrium and then you do something to change the equilibrium. This is known as LeChatlier's principle. There was a man named LeChatlier, and he was studying equilibrium reactions, and he stated something that actually makes a lot of sense, is that if you are an equilibrium reaction and a stress is applied to you, you will shift to relieve that stress. I think we all can relate. If I have a reaction that is at equilibrium, just any old reaction, A plus B in equilibrium with C and D, if it is at equilibrium, the equilibrium constant equals the concentration of C times D all over A and B. If I had any stoichiometric coefficients, they would be raised to these powers, but let's keep it simple for now. If I stress this equilibrium system, what will happen is this equilibrium will shift such that the value, the numerical value for the equilibrium constant, goes back to the same numerical value. Let's give a specific. Let's say I add some of reagent A. A is, let's say these are aqueous solutions, so A is some chemical species that's in this aqueous solution. At equilibrium it has a certain concentration, and all of a sudden I dump in more A. That means numerically this ratio is thrown out of balance. The number for A gets larger, which means the equilibrium constant gets smaller, except for it's not the equilibrium constant anymore. It's our reaction quotient because it's not at equilibrium, and so the reaction will shift to relieve that stress of adding more A. What the reaction does is it shifts to the right to use up some of that extra A that I added. The overall effect is that the amount of A will come down as the reaction shifts to the right, but it won't come down to use up all that was added. It'll only use up some of it. The amount of B will have to come down because it's also going to use up some of my B. The amount of C will go up, and the amount of D will go up as this reaction proceeds to the right. If I am observing this reaction and I can distinguish between reactants and products, let's say they're different colors, for example, I will visually observe that C and D are being produced, noted by the colors that I see, if the reaction allows it. If we think about mathematically, what happens then is that my numerical values for C and D go up, my numerical value for B goes down, and the overall effect for A is that the numerical value of A goes up. And these happen in just the precise amounts so that the numerical value of K stays constant. And so that if I recalculated this ratio using the new equilibrium values, I would indeed find I have numerically exactly the same value of K. Now the bottom line is if you add a reactant, the reaction shifts to the right to use up some of what you added such that the equilibrium shifts to the right so that the equilibrium constant remains constant. Exactly the opposite happens if you add a product. If I throw in some extra C or D, the reaction is going to shift to the left to use up some of what I threw in extra. It will produce more A and B, and the upshot is that numerically I would calculate exactly the same value for K. If I add some C or D, I might be able to observe the reaction shift to the left if I had a way to visually observe more A and B being produced. So adding a reactant shifts the reaction to use up some of what I added. And that's what LeChatlier's principle tells us. All right, now let's look at what would happen if I use up some of my reactants. So the stress I'm going to add is that I will remove some of species A. In the lab, there are lots of ways to do this. I can throw in something that reacts with A but doesn't bother anybody else. If A is a gas, I might have a way of bleeding it off. So there are ways to do this. So let's say I remove some of A. Again, if we think of our equilibrium constant, it no longer would have the same numerical value because the second I removed the A, it's not at equilibrium. But the reaction wants to go back to equilibrium, so it would shift to the left to replace some of the A that I used. It wouldn't replace all that I used. And again, if I plug in numerical values, I will find exactly the same equilibrium constant. So LeChatlier's principle says if you remove a reactant, the reaction will shift to the left to replace it. If I remove a product, the reaction will shift to the right to replace the species that I removed. And that is LeChatlier's principle as it relates to adding or removing a reactant or product.